Hello everyone, welcome to Vedanta JEE English. Okay, if you can hear me and if you can see me, please say hi and please type in clear. Today we are going to be going through one important chapter, electromagnetic waves. See, from this chapter, what the history is saying is that one question is coming almost every session. One question is coming in almost every session. So yes, it's an important thing. If you say clear, we'll start it. If you say clear, we will start it. Come on, I'm waiting for someone to respond. If you people can say clear, we'll start it. If you can hear me, please say yes. If you can see me, please type in hi, full best. If you people can hear me and if you people can see me, please say clear. Yes, full best has said that it's clear. Okay. As discussed, we will be dealing with electromagnetic waves. Okay, fine. I wanted to show some animations. That's why I have taken up the PPT rather than OneNote. Hi Varshit. Oh, you have come back here. Good man. You're a great follower of me or something like that. Okay. In JEE English, there is a crash course which has started. So those who want to be ahead of the preparation when compared with others and want some quality amount of teaching, you people can try out this particular course which has been launched recently. And you can enroll into this. Okay. Now, we'll start with this. EM waves. Right. So a brief history about this. Before detecting these electromagnetic waves, Maxwell has already proposed a theory of existence of electromagnetic waves. You can see the history over here. Around 1865, Maxwell predicted the presence of electromagnetic waves and he gave his theory around 1865. Then Hertz was the one who produced the electromagnetic waves and detected those electromagnetic waves. But the thing is, it's not mentioned in our NCERT. So we don't need to talk about Hertz experiment. What he did, I'll roughly explain to you. He generated a spark, right? And that spark has created some electromagnetic wave. That electromagnetic wave, when it went to a receiver, at the receiver also a spark got generated. Okay. And then J.C. Bose in 1894, he created those electromagnetic waves and made them travel certain amount of distance. And later you know what has happened. So this is the brief history of electromagnetic waves. Now, there will be something called as displacement current. Before we go for displacement current, we have to see what happened to the Ampere circuital law. So to understand what has happened to Ampere circuital law, what I will do is, I'm just picking a capacitor. Oh shit, this is too thin, man. Can I change the size of it? It's too thin, right? But I want to show some simulation. That's the reason why I have picked PPT today. Okay, bear with me only for today. I'll go back to the note. In the note, the problem is going to be I have to take up in the PDF form. As a result, animations won't work. Animations are not working. Let us take a capacitor, and this capacitor is going to be charged with the help of this battery. So this battery is going to be sending a current, and the current it is going to send, or the current flowing through these conducting wires, let us take it to be some IC. current flowing through the conducting wires, let us take it to be some IC. Current flowing through the conducting wires, let us take it to be some IC. Now look, what I will do is, I will take an Amperian loop. I will take an Amperian loop. This is my Amperian loop. So the Amperian loop has same radius as that of the plates. We have circular plate capacitor, and between those circular plate capacitor, I am taking an Amperian loop, and the loop's radius and the circular plate radius are exactly the same. Now, in order to use Ampere circuital law, okay, what is this one? This is Amperian loop. This is Amperian loop. In order to use this Ampere circuital law, what we have to do? We have to take area bound by the loop. So if you have proper understanding of Ampere circuital law, then you know what I'm exactly talking about. So when we have this Amperian loop, one of the area bound by this Amperian loop is taken as this green one, and I am taking that to be area A1. I'm taking it to be area A1. Okay. Now I am taking one more area. I'm just choosing some baggy area. So this baggy area is what I am choosing. So this is also the area bound by the same Amperian loop. Now for area 1 I'll write the Ampere circuital law, area 2 I'll write the Ampere circuital law. So for area 1, if I am going to talk about area 1 is this green thingy, and Ampere circuital law is closed integral B dot dl is going to be mu naught times the current that is enclosed, or the current that is going to be crossing, sum of all the currents that are going to be crossing. Now if you look at this green area, can you see any current crossing over there? Current is present in these conducting wires. So I can see the current in this wire, and I can see the current flowing in this wire, but I can't see any current flowing over there. So there is no current crossing that area. So I can say it is mu naught into 0. So the closed integral B dot dl. The closed integral B dot dl is what? The closed integral B dot dl is 0. Okay, fine. Now if I take A2 area, so that A2 area, whatever I take, can you clearly see that some current is crossing that area? Yes. So when I am going to be looking at A2 area, if I am going to take A2 area as the area bound by this blue Amperian loop, then closed integral B dot dl is going to be some mu naught into some IC. Come on, man. We are traveling on the same Amperian loop. So if we are traveling on the same Amperian loop in the case of A1 as well as A2, I should get same B dot dl. You only imagine. You assume that you are walking on this. If you are walking on this, whether you take the area bound by the loop to be A1 or whether you take the area bound by the loop to be A2, if you are walking on this Amperian loop, as you are walking on the same loop, you will come across same magnetic field. If you come across same magnetic field, then B dot dl for the loop should come out to be same. But is it coming out to be same? No. So there is something wrong with this Ampere circuital law. There is something wrong with this Ampere's circuital law. And what is that? What is that? We have to find out. That's what Maxwell has done. And for your kind information, what you have to keep in mind is that this capacitor is still getting charged. Let me draw that. Let me draw that. Let us take the charge on the capacitor to be Q, and obviously on the other plate the charge is going to be minus Q. And I know that as the charge on the plates will be changing, even the electric field between the plates will be changing. How much is that electric field? So the electric field between the plates of the capacitor is going to be sigma by epsilon naught, if you people remember. Between the plates of the capacitor is sigma by epsilon naught. And what is the sigma? Isn't it going to be Q divided by A? So Q divided by A divided by epsilon naught. So the electric field is going to be Q by A epsilon naught. Now you tell me one thing. You just tell me one thing. If these plates are going to be, if these plates are getting continuously charged from the battery, if the plates are getting charged, will the Q change? Pakka the Q is going to change. As capacitor is getting charged, as the capacitor is getting charged, as the capacitor is getting charged, Q changes. So E changes. That's when Maxwell was thinking. See, in electromagnetic induction chapter, when there was varying magnetic field produced electric field. So we have a varying electric field in this situation, then varying electric field might produce magnetic field, and Ampere missed out on that. Ampere circuital law has taken into account magnetic field produced only by the current carrying conductors. Right? Maxwell, oh, not Maxwell, sorry man. Ampere in his law has taken into account only the magnetic field produced by current carrying conductors or current carrying wires, but varying electric field is also producing magnetic field, which was not taken into consideration by Ampere. Maxwell has taken that and he finished this law, or you can say he corrected it and he gave it as Maxwell Amperean law or Ampere's Maxwell law, whatever it is. This was not taken into consideration. So then he introduced something called as displacement current, and he said that varying electric field will also produce magnetic field. So it is equivalent to how much current will produce that much amount of magnetic field which is created by the varying electric field. That he named it as displacement current, and he said that the displacement current is going to be epsilon naught d phi by dt. So whenever you are going to be coming across, a region where there is varying electric field, that varying electric field will produce magnetic field. So that magnetic field, whatever is produced, is equivalent to magnetic field produced by this ID current, right? So now let us go back and let us talk about how he has completed it. So Maxwell gave this correction. So what is the Maxwell correction? He said that closed integral B dot dl, whatever Ampere has taken, should include two parts, which is going to be the current due to the conducting wires plus the displacement current. How much is the displacement current? This is the displacement current. What is phi? Flux due to the electric field. Okay, fine. Now let us go back and see how much electric field is there in this region. We have it to be Q by A epsilon naught. So now we have chosen the Amperian loop, right? This was our Amperian loop. Now let us find out how much electric flux is associated with this. Crossing the flat area of the Amperian loop. So the flux associated with that Amperian loop is going to be electric field multiplied with the area of the loop, and that area is same as the area of the plates. I said to you, right, the Amperian loop I have taken is same size of those plates, which is what? Q by A epsilon naught into A. So A and A gets cancelled out. So phi E is going to be what? Q by epsilon naught. Now I have to talk about d phi by dt. That means here 1 by epsilon naught is constant. So automatically we have to talk about rate of change of charge on the plates of the capacitor. So the rate of change of charge on the plates of the capacitor is going to be given by what? The current that is going to be fed to the capacitor, right? Current that is going to be fed to the plates of the capacitor. So dq by dt can be written as what? IC. So I can say 1 by epsilon naught into IC is d phi by dt. So this varying electric field, whatever the magnetic field is produced by it, is equivalent to magnetic field produced by some imaginary current called as displacement current. And what is that displacement current? That displacement current is epsilon naught d phi by dt. Okay, epsilon naught into, what is that? 1 by epsilon naught into IC. So what did we get? The displacement current in this case is coming out to be equal to what? The current that is flowing through the conducting wire. Very interesting. And now it is very important for you to know where I have to take the displacement current. Like how the displacement current is going to be present between the plates. How we have to take it. This is something which is not even given in the books properly. Right? Okay. So because of space constraint, I'll just show it here itself. Whatever that ID has come, that ID, whatever I have got, is present throughout. That ID value is present throughout the volume where I have the electric field to be varying. So the total current The total displacement current ID is present in this whole area. So what is the current density? What is the current density? The current density is going to be what? It is going to be the total current divided by the area, right? Can you please tell me this displacement current is spread over how much area? It is spread over the area of the plates, right? So I can simply write it as ID by capital A, where capital A is the area of the plates of the capacitor, because the entire area of the plates of the capacitors will have the electric field, and that electric field is continuously varying throughout that area. So that as the electric field varies, we can treat it as some amount of displacement current, and that displacement current is going to be given by this as given by Maxwell, right? So this explanation you won't find it in the books. Whatever the displacement current we have got is something which is spread throughout this particular volume, and if you talk about the current that is going to be present per unit area, it is this. Now look, now let us go back and let us see whether we are going to get the answer or not, So I'll just put one extra slide. Just a second. I'll add some extra slides. Okay. Now let us go back. We got this. So what is the proper thingy now? What is the proper thingy? The proper thingy is going to be whenever you are talking about the capacitor, whatever the area might be, we have to take into consideration two currents. Now look, this is the Amperian thingy I have taken, Amperian loop. And one of the area was this flat area which I named as what? A1. And the other one was what? Other one was this baggy area what I have taken. This is that baggy area which I have taken. And I have IC flowing in the conducting wires. Right? And just now I proved, I don't know whether this will be visible or not. Just a second. The color, whatever the displacement current, no, not visible. I have to choose a different color then. Okay, I'll choose this. So I have displacement current present throughout the volume between the plates. Now look, when I am going to talk about the A1 area, what is the corrected amperes circuital law? Integral B dot dl is going to be mu naught into IC plus ID. For your kind information, for A1 area, that is this green area, I can't see any wire crossing through it or passing through it. So there is no conducting wire current for A1 area. So I can say it to be 0. But the whole ID displacement current is going to be passing through that A1 area or not? Yes. And numerically, we got that ID to be equal to what? IC. And then we have to talk about the A2 area. So when I am going to talk about the A2 area, closed integral B dot dl is going to be mu naught into, now you see, I'm talking about the baggy area. That butterfly catching nets will be there, right? So this is the brim of that butterfly catching net, and this is that net. So I can see IC crossing the net. I can see IC to be crossing the net, but I can't see any ID to be crossing this baggy area. So I have IC, but there is no displacement current crossing it. So now you get it to be what? Mu naught into IC. So once you take the Maxwell correction into account, whether you take the flat area or whether you take the baggy area, in both the situations, are you getting the same answer or not? Yes. Now the equation is complete. So what Mr. Ampere has missed on? Ampere didn't take into consideration the magnetic field produced by varying electric field. And then Maxwell came and said, yes, there will be magnetic fields produced by varying electric fields. By then, everyone are habituated to understand the magnetic field produced by currents. So Maxwell said, okay, everyone are happy and everyone are able to understand if I am giving it in the form of current. Then he said, this varying electric field is producing magnetic field, right? So same amount of magnetic field will be produced by an imaginary current called displacement current. So in reality, do we have current flowing over there? No, it's an imaginary current which has been tossed in by Mr. Maxwell to easily get the answer, nothing else. And how the displacement current is spread? It is spread throughout the volume where there is varying electric field. That's it. See, why I am going so deep into this is that these days they haven't touched it. Up to 2024 on displacement current they haven't touched it. I am strongly expecting these kind of questions if the paper is going to be tough. So look, two circular plates each of radius 0.1 meter are used to form a parallel plate capacitor. If the displacement current between the plates is 2 pi ampere, they directly gave the displacement current. The total displacement current is given, and I said to you, right, these kind of questions I am expecting, and you won't find these kind of models in regular books. In regular books, you won't find this kind of models. If the displacement current between the plates is 2 pi ampere, then calculate the magnetic field produced by the displacement current at 4 centimeters. See, we know how to calculate the magnetic field produced by current carrying wires, but now we are asked to calculate the magnetic field produced at 4 centimeters where there is no current carrying wire but there is varying electric field. Okay, done. Let's do it then. I know that this whole volume is going to have varying electric field. So the total displacement current in this region is given as 2 pi. But in that, I need only for this region. That is what I want. Now I need to calculate. So in this area, I have 2 pi. So in this area, how much I have? So what is the radius of those plates? The 0.1 meters. That means 10 centimeters. So pi into 10 centimeter square area is having how much current? 2 pi amount of current. Then pi into 4 centimeter square area will have how much current? So the current that is going to be there is 2 pi into 16 centimeter square divided by pi into 100 centimeter square. Centimeter square will get cancelled out. Pi and pi will get cancelled out. So what are you going to get? The amount of current, the amount of displacement current that is going to be crossing through this blue section will be how much? It is 32 into pi divided by 100. Roughly it is equal to 1 ampere because pi is 3.14, right? Roughly it is 1 ampere. So if I am going to take an Amperian loop, how much of displacement current is passing through? Total displacement is 2 pi, but how much will be passing through this blue section? 1 ampere will be passing. Now let us use closed integral b dot dl can be written as what? Mu naught into IC plus ID. Can you see? Can you see any conducting wire passing through this blue area? No. So there is no conducting current. Then how much portion of the displacement current is crossing this? In the total area we have 2 pi and there is 1 ampere crossing through this blue area. So we have to put it as 1. Now I can take B out, right? Then it is going to be this. So we need to talk about the total length. How much we are going to traverse, man? Radius is 4 centimeter. So how much we are going to traverse? 2 pi r. So length is going to be how much? 2 pi r, which is 4 into 10 to the power minus 2 is going to be 4 pi into 10 to the power minus 7. Right? 4 pi, 4 and pi gets cancelled out. So the B value is going to be half into 10 to the power minus 5. This much magnetic field. As I said, I haven't seen this kind of question being asked in JEE mains. I predict this question. I predict this model. I am predicting this model for JEE mains 2025 or at least in JEE advanced, because last year in JEE advanced they have added electromagnetic waves as far as I remember. So this model is something which has been ignored. As JEE advanced has put that either in JEE advanced you can expect this question or in JEE mains. If question has to be tough, only then they'll touch it, otherwise they won't touch it. Okay, now look. Now Maxwell was like, man, Ampere has missed something. Might be Gauss also has missed. So let me verify all the standard laws that have been given till now. So he verified and he found out Gauss hasn't missed anything. So what is Gauss law for electrostatic field? Was that? And that's what he gave as his first law or first equation, but he gave it in something called as del operators. But we don't have it. Divergence, curl, all those things are beyond us. So he didn't represent actually like this. He represented it in a different form called as del operator and all those things. We don't have it in our syllabus. So he verified the Gauss law and Gauss law came out to be proper and he gave that as his first equation. Now, if you talk about Gauss law for magnetic field, man, Gauss law for magnetic field is going to give you 0. Why? Gauss law is going to be for closed areas, right? And magnetic field lines always form closed loops. So if I am going to talk about a closed area, how many our field lines are going to be crossing? Those many field lines should come back because the magnetic field lines are going to be forming always closed loops. So here you can see one field line is leaving and the very same field line is entering. So net contribution will be what? 0. So Gauss law for magnetic field is this, and that is what he gave as his second equation. As I said, not exactly in this form, he has put it in a different way. As I said, del operator and all those things. And then just I think yesterday or day before yesterday, Shreyas sir has done electromagnetic induction for you. Right? In electromagnetic induction, you people have seen varying magnetic field will produce electric field, and in this class, varying electric field will produce magnetic field. So in this class, you have seen varying electric field produce magnetic field, and in the previous class, you have seen varying magnetic field produce electric field. How much electric field will be produced? This you have learned in electromagnetic induction. In this class, how much magnetic field will be produced? Just now I have done it. The varying electric field region will produce how much magnetic field has been done to you just now. Okay, this is his third. And fourth was the law which he has corrected, Ampere Maxwell's law. And Maxwell's fourth equation was closed integral B dot dl is mu naught into IC. IC is the current flowing in the conducting wires. That's why they have put C. And this is ID. And it is what? Epsilon naught d phi E by dt. These are the four equations. And using these four equations, he found the exact behavior of electromagnetic waves. So what did he say? He said that electromagnetic waves have varying electric field and varying magnetic field. The varying electric field will continuously produce the magnetic field, and the varying magnetic field will continuously produce the electric field. Like that, they self-sustain and they will travel. Like that, they self-sustain and they travel. And he gave his own theory, right? So using these four equations, he found a lot of stuff. So what are the things he found? So sources of electromagnetic waves are going to be accelerated charges, man. Accelerated charges produce electromagnetic waves. How we got to know that? Through those Maxwell equations. When he solved for them, then he found out that only accelerated charges can produce electromagnetic waves. Sir, what about the charges which are going to be at rest? If you talk about charges at rest, they produce only electrostatic field. They produce only electric field. Now, if you talk about charges moving with constant velocity, charges moving with constant velocity, charges moving with constant velocity produce electric field as well as magnetic field, but that magnetic field will not change with time. So we need to have varying magnetic field. That varying magnetic field will produce electric field, and varying electric field will produce magnetic field. Like that, they will be producing each other and they will be traveling. Okay. Now, what happens when they move with constant velocity? If they move with constant velocity, we have a constant current. Constant current is going to produce constant magnetic field, right? But we need varying magnetic field that can be produced only by accelerated charges. Keep that in mind. Sir, if we talk about LC oscillations, okay, I don't know whether AC is done or AC might be done, and you will have LC oscillations. So in LC oscillations, yes, we are going to have charges oscillating. So there will be electromagnetic waves created by any charge which is going to be oscillating. Why? If it is oscillating, it is performing to and fro motion. If it is performing to and fro motion, it is under acceleration. And yes, accelerated charges produce electromagnetic waves. There are some exceptions. What are those? Electrons revolving in those stationary orbits, they don't. Right? So some of the accelerated charges might not produce EM waves, but for sure to produce EM waves, there should be accelerated charges. Keep that in mind. So it is because of this I have taken PPT rather than what we call PDF. Or generally I take class in OneNote, right? We will get thick lines. In this PPT, we are getting thin lines. I wanted to show you this. So how an electromagnetic wave is going to look like? Man, you just focus on only the red arrow. What the red arrow is doing? The red arrow is doing oscillations, right? So that is magnetic field. And look at only the blue arrow. What the blue arrow is doing? The blue arrow is also oscillating, right? And that is electric field. So the oscillations of the electric field and the oscillations of the magnetic field are in two perpendicular planes. They are not in the same plane. So in an electromagnetic wave, electric field and magnetic field will be oscillating in two perpendicular planes. And do you notice anything interesting? both of them are reaching their maximas at the same time, and both of them are becoming zero at the same time. Both of them reach their positives at the same time. Both of them reach their negatives also at the same time. That means electric field and magnetic field are in perfect sync or not. Only thing is that they are oscillating in different planes. Only thing is that they are oscillating in different planes. But can I claim that electric field and magnetic field are in perfect sync? What do I mean? I mean that they become zero at the same time, they reach their positive extremes at the same time, they reach their negative extremes at the same time. And you can clearly see that, the electric field oscillations are sinusoidal. You can see that, right? So I can represent the electric field in the form of a sinusoidal wave, E naught, some sine, let us say kx minus omega t. Let's say you can have some phi also, initial phase also might be present, it's fine. Now one thing which you have to keep in mind is that if you have chosen electric field to be having sine, then magnetic field should also be represented with the sign and with the same phase. Why? As I said, both of them become zero at the same time. Both of them are going to be reaching their respective positives at the same time. You can see that respective negatives also at the same time. They are in perfect sync. That means they should be represented with same function and they should have same phase also. But one thing, electric field is oscillating in which direction? Y direction. Magnetic field is oscillating in which direction? Z direction. So they will be oscillating in two perpendicular planes. Right? Can I pause this one? I don't think. This is a GIF one. Okay. Now you might have a doubt. Sir, the electric field, will it be always having its direction in the positive Y? No. You see, now it is positive Y. Now it is negative Y. Now it is positive Y. Now it is negative Y. Now it is positive Y. Now it is negative Y. Let us look at B. Positive Z, negative Z, positive Z, negative Z. My intention of writing Y and Z over there is that they are along Y axis, they are along Z axis. But yes, the direction can be plus J, minus J. It can change at every point of time. So you can't say that the electric field oscillations are always in the positive J direction. After some time, they will be in the negative J direction also. So that's why while giving questions, they'll say electric field at that instant is in positive J direction. They'll clearly mention electric field at an instant is in positive J direction. Why they will say at an instant? Because it is going to be changing its direction with time. That's why. Is everyone clear? Okay. Now let us look at some of these properties, man. Now let us look at some of the properties. What are those properties? We got to know that electric field will be perpendicular to the magnetic field and both of them are going to be oscillating with same function, with the same function and same phase. Now, I don't know whether you have noticed it or not. Electric field is oscillating in Y, magnetic field in Z, wave is propagating in X. See, X is perpendicular to both Y and Z or not. So the direction of propagation of the EM wave will be perpendicular to the direction of electric field as well as direction of magnetic field. Now you only tell me, can you find out the direction? Can you find out the direction? All you have to do is what? At a particular instant, at a particular instant. Let's say when the E is along Y and when the B is along K. What is J cross K? J cross K will be I, right? When the electric field is in the J direction, magnetic field is in the K direction. So what does J cross give us? What does J cross K give us? I cap. So the direction of propagation of the direction of propagation of EM wave is same as the direction of E bar cross B bar. Keep that in mind. Many times question has been asked on this. For example, let me give you one question. One example. At an instant, electric field is in I cap direction, magnetic field is in K cap direction. Find the direction of propagation of EM wave. As I said, the direction of the EM wave is what? Same as that of the direction of E bar cross B bar. Same as the direction of E bar cross B bar. Yes. Okay. What is E bar? It is I cap. What is I cap cross K cap? We have that shortcut, right? I, J, K. So if you do I cross J, you will get K. If you do J cross K, you will get I. If you do K cross I, you will get J. If you go reverse, then negative. So I cross J, I cross K. I cross K indicates what? Minus J. So the electromagnetic wave is traveling in negative Y direction. That means the energy is going in the downward direction. Okay, sometimes what kind of questions they are going to ask? They give the direction of EM wave. At an instant, the electric field is let's say is in J cap direction, and EM wave is in K cap direction. Find direction of B bar at that instant. These kind of questions can also be asked, right? So direction of EM wave. Is going to be what? Direction of EM wave is going to be given, is going to be having same direction as E cross B. I know that the direction of EM wave is K. E is going to be J. So now you only tell me what should be the direction of B such that the cross product of J as well as this bracket will give us K. Man, if it is J cross I, we will get minus K, but I need plus K. So it should be J cross minus I cap. So J cross I gives you minus K and minus I cap gives you plus K. So the direction of the magnetic field at that instant is minus I cap. Those who are having doubt, always keep one thing in mind, man. If you have J and K, the other one should definitely be I. Whether it is plus I or minus I, you have to use your common sense. So I know that definitely it is I. So J cross I, if it is going to be I, then J cross I should be minus K, but they have given it to be K. That means it is not J cross I, it is J cross minus I. That's how you have to use your common sense and do these questions. But as I said, majority of questions are on direction. Majority of questions are on direction. Keep that in mind. Next. Few more properties, man. What we got as of now, we just got to know the direction of the electric field, magnetic field, and the direction of the EM wave. Few more relations. E naught by B naught. What is E naught? Amplitude of the electric field, the maximum electric field it can reach to. B naught is the maximum magnetic field it can reach to. So, we have a relation. What is that? E naught by B naught is equal to the wave speed. If EM wave is traveling in vacuum or in free space, then E naught by B naught, which is wave speed, and we know the wave speed to be equal to C in vacuum or not. Speed of light. Okay. Not needed, Mr. Ish. You blindly follow this. Blindly follow this. See, some people are thinking of using Fleming's left-hand rule. Fleming's left-hand rule has come from cross product only. Right? Here we are doing cross product. So those who want a shortcut, E cross B, right? Look, your middle finger should be E, your index finger should be B, thumb points the direction of the electromagnetic wave. So those who want to use Fleming's left-hand rule as a shortcut for this one, middle finger should be E, index finger should be B, and thumb is going to point the direction of electromagnetic wave. That's a shortcut, but as I said, you better use this rather than this, because in examination, rotating your hand like this is going to be difficult. Rotating your hand like this, doing stunts in the examination is going to be difficult. So that's why you better stick to this one and you write like this. Okay. Sir, then what is the speed of the electromagnetic waves, sir? See, if the wave equation is given, to find speed of EM wave, if wave equation is given, then the wave speed can be calculated as, we have just seen waves, right? Like last week only we have completed waves. How to get the wave speed? Coefficient of t by coefficient of x. Coefficient of t by coefficient of x, which in turn will become omega by k. But sometimes they don't give that. What they are going to give? They are going to give epsilon r and mu r. Sometimes epsilon r, I hope you people remember, epsilon is what? Permittivity. Epsilon r is relative permittivity and mu r is relative permeability. Sometimes epsilon r and mu r are given. Then how do we find it? So the electromagnetic wave speed, in that case, is 1 by under root of mu of the medium, epsilon of the medium. This is the wave speed. Sir, they are giving information about mu or epsilon r, sir. You said that it is mu n and epsilon m, sir. Mu m is permeability of that medium. Epsilon m is permeability of, permittivity of that medium. Sir, they haven't given information about this, sir. They have given information about mu or epsilon r, sir. Yes, we can convert it in free space. In free space, the wave speed is going to be 1 by under root of mu naught epsilon naught. Mu naught is permeability of free space, epsilon naught is permittivity of free space. Now, if you want in some medium, then V is going to be what? 1 by under root of mu m epsilon m. Right? Now what am I going to do? Let us see that. Let me just look at that. If I am going to do, let us say, C by V, C by V, then what do I get? Root, this will go to the numerator, this will be in the denominator. It will become mu m epsilon m by mu naught epsilon naught. What is mu m by mu naught? Mu r. What is epsilon m by epsilon naught? Epsilon r. So C by V is going to be a root mu r epsilon r. So if you are ever in need of finding the wave speed in a medium when they have given epsilon r and mu r, this is the formula you people have to use. This is the formula you people have to use. Keep that in mind. Okay, fine enough. Okay, sir. We dealt with in which direction the electromagnetic wave is going to move. With how much speed it is going to move. All those things are done. But electromagnetic wave generally does what? It carries energy. Sir, how much energy is carried by it? But before we go for that energy, sir, individually you first tell us electric field. How much energy is stored in the form of electric field? How much energy is stored in the form of magnetic field? First, let us talk about that, sir. Okay, we know the energy density. What is the energy density in the form of electric field? Half epsilon naught E square. This has been given to you long back. Even for magnetic field also, half B square by mu naught was given to you. Right? Now, man, as this E is going to be continuously changing. How? It is E naught sine kx minus omega t. So the amount of energy stored in the form of electric field is continuously changing. Sir, I don't want to learn that. Averagely, how much is there? That you give me. So, average UE for one cycle. How much energy is stored in the form of electric field for one oscillation of electric field? Averages will be represented with UE. So, like this symbol, just a second, man. How to find average of anything? It is integral UE into dt by integral dt. For your kind information, we have to integrate from 0 to t, that is one cycle, one time period of time. As a result, see, half is a constant, epsilon naught is a constant, E naught is a constant, we can take it out. So half epsilon naught E naught square integration of sine square kx minus omega t into dt by integral dt, where to where? 0 to capital T, 0 to capital T. Man, I am not wasting your time. Look, integration of this one is going to come out to be half. Integration of this one is going to come out to be half. I'm saving your time. And in fact, even integration of cos square also will come out to be half. You don't need to worry for one complete cycle. So whenever you come across sine square or cos squares, you will come across this even in AC also. So whenever you see integration of sine square or cos square by integral dt thingy, you write it as half. So what happened? What is the average energy density in the form of electric field? It is 1 by 4 epsilon naught E naught square. This much. 1 by 4 epsilon naught E naught square. Okay, fine. Sir, you gave us averagely how much energy is stored in the form of electric field, sir. How much is stored in the form of magnetic field, sir? Same story, man. The amount of energy stored in the form of magnetic field, energy density, that means energy per unit volume, is half B square by mu naught. So if you want the average of it, obviously it is going to be integral ub into dt by integral dt. Man, I'm saving time. You know, we have to represent b as b naught sine kx minus omega t. You will get the same story again. You will get integration of sine square, and integration of sine square by integral dt will result in half. So what do you get here? You get 1 by 4 b naught square by mu naught. Now some people are going to be like, sir, I'm interested in checking something. What is it? What is that you are interested in? Sir, I am interested in checking when the wave is traveling, will it store more energy in the form of electric field or will it store more energy in the form of magnetic field? So EM wave, electromagnetic wave, is an energy. So that energy is stored majority with E or majorly with B. That's what we want to check. Okay, fine. Let's do that. Let's do the comparison. What do we have? We have 1 by 4 epsilon naught E naught square. Man, we have E naught by B naught for free space can be written C. So I can write B naught as E naught by C. So now the average energy in the form of magnetic field 1 by 4 B naught square, right? It will turn out to be what? E naught square by C square into mu naught. Man, 1 by C square will be what? You only think. Where is it? Yes, this is C. Then C square will be what? 1 by mu naught epsilon naught. Then 1 by C square will be what? Mu naught epsilon naught. Let us put that. 1 by 4. 1 by C square. Mu naught epsilon naught into E naught square by mu naught. Mu naught gets cancelled out. You get it to be half epsilon naught E naught square. Interesting. Look at the amplitudes ratio. Man, electric field is way dominating than the magnetic field. How I know? Ratio is 3 into 10 to the power 8. So the amplitude of electric field is very big when compared with the amplitude of magnetic field. But still, same amount of energy is stored. Why? This is the energy in the form of magnetic field. I think exactly the same thing we have got for electric field also. So electromagnetic wave is not showing any partiality. It is storing energy equally in the form of electric field and in the form of magnetic field. Okay, super. Now we got to know that. We didn't get to know the total energy density of the electromagnetic wave, which I am going to do anyway. But we got to know whatever the energy is there, that energy density is equally split between electric field and magnetic field. That much clarity we got. Happy. What is the total energy density then? Oh shit. I'm overdoing stuff, man. Ding, ding. I have left few slides, but I have taken more. Okay. Then what is the total energy density? The total energy density associated with an electromagnetic wave. What is energy density? The energy present per unit volume. So that is the energy density in the form of electric field and the energy density in the form of magnetic field. So I am talking about average. So electric field wala half epsilon naught E naught, not half, my bad, 1 by 4. And magnetic field wala 1 by 4 B naught square by mu naught. And for your kind information, this came out to be exactly this one. So you can write it. So 1 by 4 epsilon naught E naught square plus 1 by 4 epsilon naught E naught square, which will result in as this. This is the energy density of the total electromagnetic wave. Energy density of the total electromagnetic wave. Okay, fine. Now there will be something called as Poynting vector. Poynting vector represented with the symbol S bar. What does this give us? It is going to give us rate of flow of energy per unit area. Rate of flow of energy per unit area. Man, this sounds like intensity, na? Rate of flow of energy is power. Power by area is what? Intensity. So basically this Poynting vector is giving you how much intensity of electromagnetic wave we have. So that energy is going to be given by E bar cross B bar divided by mu naught. This is Poynting vector. Okay, name is different, but what it gives us? It is going to be giving us intensity, man, indirectly. Now you tell me, if I'm going to talk about the magnitude of this S bar, I will represent with S. In fact, I'll represent it with I, because it is just like intensity. So Poynting vector gives us intensity. And what is that? It is equal to E bar cross B bar. What is the angle between E and B? What is the angle between E and B? 90. So you can simply write it as EB sine 90 divided by mu naught. So the intensity or the Poynting vector is going to be E naught sine kx minus omega t. And then we have B naught sine kx minus omega t divided by mu naught. Now E naught into B naught by mu naught sine square kx minus omega t. So the actual intensity of the electromagnetic wave is continuously changing, man. The actual intensity is continuously changing, sir. No. And that change will be automatically, it is going to be very fast. So I want to talk about averages. So when I want to talk about average intensity, and in fact this is what you have to use in questions, man. After the direction of propagation of the wave, EM waves, next important is going to be intensity of the EM wave. Next important thing is going to be intensity of the EM wave. Okay, fine. What is the average? Obviously any average is going to be given by this. So when I am trying to do this, again we have sine squared. Again we have sine square. Okay, let me write that. So the average intensity of the electromagnetic wave is, we are almost done with the theory, man. We will start with the questions. E naught B naught by mu naught is a constant. And then we have sine square. So we have integral sine square kx minus omega t into dt by integral dt, where to where I want to find out what is the average intensity in one cycle. So this part I already said to you, this will turn out to be half. So it is half E naught B naught by mu naught. This is the intensity, man. This is the intensity. Now what I will do is, I will just multiply c square and I will divide c square. 1 by c square can be written as what? 1 by c square can be written as what? Mu naught epsilon naught. Okay, let me write that. Half E naught, and B naught can be written as what? E naught by C divided by mu naught. You keep that upper C square as it is, but that 1 by C square, you write it as mu naught epsilon naught. So mu naught and mu naught are going to get cancelled out. 1C and 1C are going to get cancelled out. So the average intensity is half epsilon naught E naught square into C. A formula worth memorizing. A formula worth memorizing. And yes, we have a lot of questions coming on this. Okay. Now, let us start solving questions. Let us look at all the PYQs that have been asked. So there won't be a separate PYQ session on electromagnetic waves as the chapter is small. I have covered almost the whole theory. In fact, after solving the numerical questions, I have taken up theoretical questions, and the theory, whatever is needed, I have personally copied it from NCERT. After this class, you don't even need to read the NCERT. I will cover up everything. I will be covering up everything. So let us do these questions then. Given below are two statements. Statement 1, electromagnetic waves are not deflected by electric and magnetic field. Yes. They are not going to be responding to electric fields as well as magnetic fields. That's true. That's a property. The amplitude of electric field and the magnetic field in the electromagnetic waves are related to each other. Wrong, man. Why? E naught by B naught is going to be C. What is C? 1 by under root of mu naught epsilon naught. Can you see 1 by under root of mu naught epsilon naught? No. That means this one is wrong. So those people who don't have clarity about statement 1, they can clearly see that the statement 2 is wrong. So statement 2 is false, statement 1 is true. So basically at least two options will be eliminated even if you know only statement 2, because statement 2 is definitely wrong. So these two are ruled out. And electromagnetic wave is something which is not going to be responding, or it won't experience any force due to electric field or magnetic field. Anupam Reddy is asking a question. Sir, I am doing right now for JEE mains. Can I watch these videos later? Will it be there, right? See, these videos are going to be recorded, but for JEE mains, this is very important, man. For JEE mains, this is very important topic. This is not an advanced topic. Okay, next. For a plane electromagnetic wave given by E is equal to E naught sine omega t minus kx and B is equal to B naught sine omega t minus kx, ratio of average electric energy density to the average magnetic energy density. Blindly mark one. Blindly mark one. All these are PYQs only. 2024 PYQs have been picked. 2023 also, some of them I have picked because I wanted to cover all the models. So after today's class, you don't need to visit any other place to do EM waves. Everything is sorted out here itself. Okay. So the average electric density and average magnetic field density is going to be one, reason being they store energy equally. Sumati, you have to look at. Okay. Next, one more question. In an electromagnetic wave, at an instant and at particular position, the electric field is along negative z direction, man. So the direction of the electric field is in negative z direction. That means minus k cap. Magnetic field is along positive, and they're asking in the direction of propagation of the electromagnetic wave. Man, direction of EM wave. If I talk about direction of the electromagnetic wave, is going to be given by what? E cross B, right? E cross B, right? So we need the direction. So this is minus K and B is I. So what is that shortcut which I have given to you? I, J, K. I cross J is K, J cross K is I, K cross I is J. Now look, K cross I gives you J, and we have one minus also. Let us write that minus. What is K cross I? It's J. K cross I is J. So now you can see that the direction of propagation of the electromagnetic wave is negative J direction. Negative J direction means negative y-axis. As I said, majority of the questions are going to be on the direction of propagation, right? Sometimes they are going to be on intensity, basically on properties of electromagnetic waves. That's why I said to you, very rarely they have asked questions on displacement current. There is every possibility that the displacement current can be asked. If they want to ask it as a tough one, only those people who have listened to me, I have picked a good model, only those people are going to be getting benefited. So the beginning of the video I have covered that model. If frequency of electromagnetic wave is 60 megahertz and it travels in air along z direction, then the corresponding electric field and magnetic field vectors will be mutually perpendicular to each other, and the wavelength of the, man, they gave some long story, man. All that story is not needed. All that story is not needed, right? They gave frequency. They are saying that it is traveling in air. So you need basics of waves. Frequency of a wave is going to be given by what? Speed by its wavelength. They are asking wavelength. So wavelength is going to be speed by frequency. Hi Luna. Okay. Speed in air is going to be what? 3 into 10 to the power 8 divided by, what is the frequency? 60 megahertz. That means 10 to the power 6. So 10 to the power 6 and 1 0, you will be left with what? 10. So it is going to be 30 by 6, which is going to be how much? 5, man. It's going to be 5. So what's the answer? 5. 2024. Okay. Now let us look at this. The electric field of an electromagnetic wave in free space is represented as E bar is what? E naught cos omega t minus kz. Okay, fine. But do you see? Look, there is a lot of information in this part. Till now it was kx minus omega t or omega t minus kx. So that x indicates it's a wave traveling in positive x direction. Now here we are talking in terms of z. So coefficient of z is negative, coefficient of t is positive. I personally has covered waves And I have already given you how to identify in which direction the wave is traveling. You can see Z, coefficient of Z and T are in the having opposite signs. So it's a wave. The EM wave is traveling in positive Z direction. That means it's traveling in positive K cap direction. So we know the direction of EM wave. Now they are talking about what? Corresponding magnetic induction vector will be. Right? Man, wave is in K direction, electric field is in I direction, then magnetic field should be in J direction. And one more thing, electric field and magnetic field will be in perfect sync. That means the function should be same. Okay, so where all I have same function, everywhere I have same function except this and this. Why? I should get cos omega t minus kz. Cos omega t minus kz is there only in two options. Now, so b bar is going to be b naught into cos omega t minus kz. I need the amplitude of this. I know that E naught by B naught is equal to C. So I can write B naught to be what? I can write B naught to be E naught by C. Done. Where you have amplitude as E naught by C, which option? Yes, I have option B. Super. Sumati super. Luna super. Rahul Dev. Okay, one second. Before I read a comment, you people keep trying this question. राहुल देव जयपुरिया सर मैं इंजीनियरिंग सेकेंड ईयर मेटलर्जी ब्रांच मैं 2023 में जेईई और बोर्ड एग्ज़ाम दिया था और इंजीनियरिंग 2023 में एडमिशन किया था। आपका चैनल देख के बहुत हेल्प मिला था। थैंक यू मैन, थैंक यू एंड यू आर वेलकम। An electromagnetic wave of frequency, they give frequency, is propagating along Z axis. The amplitude of the electric field is 4 volt per meter. And the average energy density, man, average energy density of electric field. What was the average energy density of the electric field? It was 1 by 4 epsilon naught E naught square. So 1 by 4 epsilon naught value also they have given 8.8 into 10 to the power minus 12 into E naught square. What is the amplitude? 4. So 4 square. So I can cancel out 1 4 and 1 4. Then it is 8.8 into 4, right? What is 8.8 into 4? 33.2. Let me cross check. 8.8 into 4, 35.2. 35.2 into 10 to the power minus 12. So how many options? 35.2 into 10 to the power minus 12. Yes, we have only one option, which is option C. Yes, Sumati. Sorry. Yes, Praveen. Yes, it is enough. It's enough, man. Take one more. A lamp emits monochromatic green light uniformly in all directions. The lamp is 3% efficient in converting electrical power to electromagnetic waves and consumes 100 watts of power. Man, it might be consuming 100 watts of power, but only 3% of 100 watts is converted to EM waves. Is converted to EM waves. Is converted to EM waves. %3 means what? 3 watts of EM wave. 3 watts of EM wave. 3 watts of EM wave has been generated. Oh, we got Anil. Welcome back, man. Okay, I have got the power. Okay, now. Sorry. Amplitude of the electric field associated with the electromagnetic radiation at a distance of 5 meters. So, They're asking electric field, they gave power. How do we do it? Look, you just take this to be that light, and this one is going to be sending out whatever the power it has consumed and emitted in the form of light is going to go in all the directions. Now I want at what distance? I want at a distance of 5 meter. I want at a distance of 5 meter. I know how much power this is sending in the form of light. So the intensity is going to be what? Intensity is going to be the power divided by the area on which the power is going to fall. So how much power? 3 watts. What is the area? 4 pi 5 square, because it falls on a spherical surface and it is 5 meters. So done. So what do we have? We have the intensity to be 3 into 4 pi into 25. So it is 3 by 100 pi, but that intensity is half epsilon naught E naught square into C. So from this you have to calculate the E naught value. You know the epsilon naught value, you know the C value. From this you have to calculate the E naught value. Do the math and find out. You can do the rough calculations because there is a big difference. 1.34, 2.68, 4.02, 5.36. As the difference is big, you can do rough calculations. So this is what you have to simplify. C is 3 into 10 to the power 8. Epsilon naught is 8.8 into 10 to the power minus 12. Right? You can take. And then pi 3.14 roughly. From there you can get the E naught value. Okay. The calculation part, I'm just trusting you people that you people will be doing it. Now look at this question. An electromagnetic wave traveling in x direction has frequency of 23 into 10 to the power 14. They gave the frequency. And the electric field amplitude is 27 volt per meter. From the options given below, which one describes the magnetic field for this wave? Okay. No information about the directions have been given, right? So we just need to talk about frequency. From the frequency, we will be getting the omega. From the frequency, we will be getting the omega value, right? They gave the frequency as 23 into 10 to the power 14. So the frequency is given as 23 into 10 to the power 14. And that frequency is what? Omega by 2 pi. So what is the omega then? 23 into 2, which is 46 pi. Or you can say 23 into 2 pi into 10 to the power 14. Let us look at the options where the omega is 23 into 2 pi into 10 to the power 14. How many options? None of the options. Something is wrong. They should have typed it, right? You can write it as what? 2 pi into 23 into 10 to the power 14 is what we can write. So basically I can see that there is 2 into 10 to the power 14 here, 2 into 10 to the power 14 here, 2 into 10 to the power 14 here, but it should be 23, right? This is wrong. There is no 2 pi at all. Now in these options, as they have given the electric field, can we get the magnetic field amplitude? Yes. We know that E naught by B naught is going to be what? C. Now you only tell me, what is the E naught, man? E naught is given as 27. So 27 by B naught is going to be 3 into 10 to the power 8. then what will be the B naught value? It is 27 by 3 into 10 to the power 8, which is going to be 9 into 10 to the power minus 8. I have to see how many options has B naught as 9 into 10 to the power minus 8. We have 9 into 10 to the power minus 8. We have 9 into 10 to the power minus 8. Okay, till here also it is fine. But man, they say x direction, that is also fine. So our answer is going to be between this option and this option. This is ruled out. Why? Why C is ruled out? This is one of the best questions. Very less information is given. They are expecting us to calculate everything. Why B is ruled out? Man, we have the electromagnetic wave traveling in X direction. If wave is traveling in X direction, how come magnetic field be in X direction? Wrong, right? So this leads us to have only one option to be correct, that is option B. Why? See, same amplitude they have, amplitude we calculated, but the problem is, as the wave is traveling in X direction, magnetic field should not have its direction in X. It should be either in Z or in Y. It should be either in the Z direction or in the Y direction. Okay, because E, B and electromagnetic wave, all three of them should be mutually perpendicular. Should be mutually perpendicular. Okay, fine. Next question. Next question. I'll drink some water. Next question. For a plane electromagnetic wave, just read the question. I'll be back. Just drinking some water. For plane electromagnetic waves propagating in the Z direction, which one of the following combination gives the correct possible direction of EB? Man, they said that it's in Z direction. We have to see which one is going to give us K cap or minus K cap, whatever it is. The cross product should give us K direction. E cross B should give us K. Now look, if I am going to talk about option A, I have left a slide, so I'll just talk about option A. So option A, E bar cross B bar is what I do. Then what is the E? I cap plus 2j cap cross, what is the B? B is 2i cap minus j cap. And you know one thing, the shortcut is this, ijk thingy, I cross j is k, j cross k is I. Now look, I cross I, like I cross 2i, I cross I is going to be what? 0. I cross j will be what? I cross j will be k, but you have minus 1. So you get minus k. Now, 2 into 2 will be 4, j cross I will be minus. So 4 into minus k, j cross j will be what? Anyway 0. So what is the direction of this one? Minus 5 k cap. So 5 into minus k cap. See here, they are not precise. When they say z direction, first option is giving me in the minus k direction. That is minus z direction. If there is any option which is going to give me plus k cap direction, then I will mark that. If there is no option giving me first plus k cap, then only I will think of minus k. Here they should have been properly saying that it is traveling in positive z direction. They should have said that it is traveling in positive z direction. Okay. Let us check for option B. When I am going to be looking for option B, so how about option B? So in the option B, we have minus 2i cap minus 3 and 3i cap minus 2. So we are talking about E bar cross B bar. We have minus 2i cap minus 3j cap cross 3i cap minus 2j cap. Let us do this cross product and check whether we will get k cap or not. So I cross I anyway will give you 0. I cross j will give you k, but you have minus 2 and minus 2, which will become what? Plus 4. So plus 4 k cap. And then j cross I will give you minus k, minus 3 into 3, which will be minus 9 into minus k. So you'll get it to be 13 k cap. Then you better mark option B only. So they should have been precisely talking about plus G direction. Option B has given me that. Option B has given me that. Okay. Next. Look at this. This is also 2024. As I said, the chapter is small, so I am completing all the PYQs also in this class itself. Okay. The magnetic field in a plane electromagnetic wave is, okay, the corresponding electric field. Man, the very first thing you have to do is magnetic field and the electric field should have exactly the same function, right? And one more thing, you can see here x, coefficient of x and coefficient of t are having same sign. That means it's a wave traveling in negative x direction. It's a wave traveling in negative x direction. Okay, fine. I should have same function. Where are those options having same function? Same function, same function, same function, same function. They're smart, man. Everything is same. Now look, as B is in Y, wave is in I, so pakka electric field should be in Z, because E, B and direction of EM wave should be perpendicular to each other. So B has taken Y, wave has taken X thingy, then automatically electric field should be in Z direction. So how many of the options have Z direction? Yes, I have option A and I have option D. Now, can I get the amplitude? Yes, I can get the amplitude. E naught by B naught is going to be the wave speed. How to get the wave speed? It is going to be coefficient of t by coefficient of x, which is 0.5 into 10 to the power 11 divided by 1.5 into 10 to the power 3. So what do you get? You get 1 by 3 into 10 to the power 8. Man, many people will directly take it to be 3 into 10 to the power 8, but that is not the case over here. Always keep in mind, E naught by B naught is going to be the wave speed. Now, what is the E naught? E naught is going to be 1 by 3 into 10 to the power 8 into B naught. What is the B naught value? 3.5 into 10 to the power minus 7. So basically it is going to be 35 by 3. 35 by 3. Oh shit. None of the options have 35 by 3, man. 35 by 3 will be what? Did I do any calculation mistake? It is 3.5. 35 by 3 will be what? Some 11 point something. So this is not having 11 point something. But this should not be 1.17. It should be 11.7. Then you are going to be marking it as D. It's not B. Shenmugan, not. Because they shouldn't have typed it as EY. It should be EZ. It should be EZ. Right? This should have been 11.7, man. 11.7. I haven't done any calculation mistake. I don't think so. I can't see it. 1.5. 0.5 10 to the power 11 by 1.5 10 to the power 3. Yes, 35 by 3 is the amplitude. 35 by 3 is the amplitude. Okay. Next, this one. A plane EM wave is propagating along x direction. Okay. It has a wavelength of 4 millimeter. If the electric field is in y direction with a maximum amplitude of 60, the equation of the magnetic field. The very first thing you people should look at is that, see, EM wave is in x direction, electric field is in y direction, then magnetic field should be in z direction. How many options have z direction? See, we have A, we have B, we have C also, but this is wrong. Right? So now, if I am going to be talking about amplitude, two options have same amplitude, third option is having a different amplitude. Let us try to find out that amplitude. But these people, they haven't given in which medium it is traveling. But from the options, I can see coefficient of t and coefficient of x. From there, I can see in all the three options, the wave speed is 3 into 10 to the power 8 only. I'm lucky. All the options have same wave speed. They haven't mentioned in which medium the wave was traveling. Okay, fine. E naught by B naught is going to be what? C. I need B naught. It's going to be E naught by C. What is the E naught value? It is 60 divided by C, which is 3 into 10 to the power 8, which is going to be 2 into 10 to the power minus 7. Which option has 2 into 10 to the power minus 7? This option and this option. So this is also kicked out now. Now we have to check which one is going to be suitable. So you multiply this inside, then what is the K value, man? See, actually we say Kx, right? So if you look at that first option, for option A, the K value is how much? Pi by 2. And K is what? 2 pi by lambda is pi by 2. Pi gets cancelled out. Lambda is what? 4 meters. Not millimeters, 4 meters. But they gave the wavelength is 4 millimeters. That means option A is also wrong. Then which option is correct? Option B is correct. Option B is correct. Okay, fine. Next. Look at how many questions have been asked. Electromagnetic waves travel in a medium with a speed of 1.5 into 10 to the power 8. The relative permeability of the medium is 2. Relative permittivity is asked. I already gave you this. Speed of the electromagnetic wave is C by under root of mu r epsilon r. So what is the speed given as? It is given as 1.5 into 10 to the power 8 is 3 into 10 to the power 8 divided by mu r is given as 2. They are asking epsilon r. So this one and this one, you can say like this. Then when you do squaring, 4 is equal to 1 by 2 epsilon r. Epsilon r is what? 1 by 8. Bad boy. Why I said bad? Why did I say it to be bad? Because I did a calculation mistake. This is 2. So when you do squaring, you'll get 4 here. And then 4 by 2 will be what? 2. So epsilon r is going to be how much? 2. So which option is having epsilon r as 2? This option. C option. Option C. Very good, Mr. Arjun. Good. Next. I said to you, right? I will cover the whole NCERT also. If there are any theoretical questions, even theoretical questions are going to be covered. That's what I said to you people. So I have to keep up my promise. So when I'm going to talk about these electromagnetic waves, all the electromagnetic waves whatever possible electromagnetic waves have been classified into categories, right? now now radio waves are those, okay, radio waves are those ones which are going to have highest wavelength, man. Highest wavelength will be with the radio waves, lowest wavelength will be with gamma rays. Keep that in mind. Keep that in mind. Lowest is going to be with gamma, highest is going to be with radio waves. They will do the comparison, man. I am not expecting you to memorize. I'm not expecting you to memorize the exact wavelengths, but yes, I am expecting you to know which one has more wavelength, which one has less wavelength. Whichever is going to have more energy, that is going to be having less wavelength. Keep that in mind. Gamma is going to be the dangerous one, and that's the one which is going to have more energy, so less wavelength. Keep that in mind. Next, microwaves. After radio waves, microwaves will have less wavelength. And then we have infrared, and then we have visible light, and then we have UV, and then we have X-rays. So if you ask me, as we go down, wavelength decreases, energy increases. If something is having more energy, they are more dangerous. We know that UV is dangerous. Then the wavelength of UV will be less than visible light, or more than visible light means less than the visible light. Right? And so you can see, as you go down, wavelength decreases, energy increases. Now what I have seen over the years is that they are asking, man, they are giving match the column kind of questions, and they are asking how the radio waves are going to be produced. So production, the radio waves are produced by rapid acceleration and deceleration of electrons in aerials. You have to mug it up. Production of EM waves by accelerated charges. Literally, those accelerated charges produce radio waves. Now, microwaves. Man, Clytron valve, or magnetron valve. What are these things? These are some vacuum tubes kind of things, man. So in those, you are going to get microwaves. We will talk about microwaves in detail and how they are going to be detected. Look, radio waves are going to be detected by the receiver antennas or receiver aerials, and microwaves are going to be detected with the help of point contact diodes. You have to keep these things in your mind roughly. If one or two are going to be memorized also, as mostly they are going to give a matrix matching thingy, you can eliminate the options and you can get them. So I'm not expecting you to completely by heart them. Obviously you are going to be forgetting, but have a rough idea. Okay, now infrared is going to be produced by vibration of atoms and molecules. Basically a body which is going to be having some amount of temperature, hot bodies, the radiation they are going to be emitting is going to be falling in the infrared region. Okay, how they are going to be detected? By thermopiles or infrared photographic films, bolometer. These are all some devices which you don't need to understand exactly how they are going to work. They are not in our syllabus. You just know them that okay, this is how we detect them. Roughly have an idea. Now, visible light. Electrons in atoms emit light when they move from one energy to the energy level. Man, if you talk about hydrogen atom, in hydrogen atom in Balmer series, whatever the light is going to come is going to be in the visible region. So electrons jumping from one state to the other state, they give away photons, and those photons, if their wavelength is going to be in the range of visible, yes. Now, how we detect the visible light? Our eyes can do that. Photocells or photographic films. Next, UV, dangerous. All the ones which are below are not dangerous. Beyond light, wavelength decreases, energy increases, UV is dangerous. Inner shell, electrons in atoms moving from one energy level to the lower energy level. Why they are talking about inertials? Because the energy gap will be more. If the energy gap is going to be more, then the photons coming out are going to be more, are going to be having more energy. More energy means they are dangerous. Now, how they are going to be detected? With the help of photocells or with the help of photographic films. Next, X-rays. You know how X-rays are going to be produced in the X-ray tubes, and characteristic X-rays are going to be produced by K transition, L transition, like that, right? So the electrons which are going to be in the orbitals which are closer to the nucleus are going to be knocked out, and that place will be filled. That place will be filled by the electrons coming from the higher orbits. So in that situation, if I take a heavy atom, like atomic number is going to be big, then the energy gap between the levels will be even bigger. If it is going to be even bigger, then the energy of the photon coming out will be even bigger, wavelength will be less. Yes, X-rays are going to be produced by heavier atoms, and that too transition in the inner shells, K shell, L shell, all those things. How they are going to be detected? Ionization chamber is a famous one. Now gamma. When gamma is going to be produced, man, in radioactive decay, whatever the nuclei that got formed, if that nucleus is in higher excited state, it will de-excite. When it is going to be de-exciting, that's when it is going to be emitting energy, and that energy is called as gamma radiation or gamma energy. Okay, fine. Now we realized who are going to be producing what radiation, but we have to individually talk about these things, because there are some theoretical bits put into that, some theoretical questions put into that. Some theoretical questions have been put, so that's why I will highlight the portions which you people have to keep in mind. See, radio waves, as I already said, are going to be produced by accelerated motion of the charges in the conducting wires. Okay, now they are used in radio and television communications, man. And now you have to look at the range of frequencies. Yes, the amplitude modulated one is going to be 530 kilohertz to 1710, and higher frequencies, look, 54 megahertz are used for short wave bands. TV wave ranges from 54 megahertz to 890 megahertz. So what I have seen, although communication system has been kicked out, deleted for our syllabus, but as EM waves is there, I have seen they are going to ask what is the range of frequencies for TV waves. Keep in mind that they will be in megahertz. Next, cellular phones. Cellular phones use radio waves, and they are going to be called as, yes, ultra high frequency band. So whatever the highlighted ones are there, those are the ones which you have to have a rough idea about. Don't mug them up, anyway you'll forget. These notes will be shared to you before your examination. Just go through these underlined things and go. Okay, next, microwaves. So microwaves, short wavelength, they are going to be having wavelength lesser than radio waves. So when compared with radio waves, microwaves are bit more dangerous because they have less energy. Look, so where microwaves are produced? In special vacuum tubes called klystron or magnetron or gun diodes. Now, due to their short wavelengths, they are suitable for radar systems. If they are going to ask what will be used in radar systems, It's not radio waves, it's microwaves. Used in aircraft navigation. Yes. So speed guns. In cricket, right? They say, okay, this has been delivered with 150 kilometers per hour and all that stuff. So how they are going to be measuring? With the help of speed guns, and the basis has been taken from these radar, and in radar we have microwaves. Okay. Yes, microwave ovens are, one second. What will happen in micro ovens? I'll just explain you. So the food atoms are, or the food particles are going to have some quantity of water in them, and that water is going to be having certain frequency of its oscillations. So now this micro oven, what it does, it produces electromagnetic waves of same frequency as the natural frequency of oscillations of water. Then these EM waves have same frequency as the frequency of natural oscillations of the water. And when they are going to go and meet, there will be resonance. As a result, what will happen? The amplitude of oscillation of the water particles is going to be increasing. That means you are increasing the energy. Increasing energy is nothing but you are heating it up. That's how when you put a bowl into the micro oven, the bowl is not going to get heated up, but the food inside it is going to get heated up, because the food is going to have water molecules, and the oven is designed in such a way that it will produce frequency of EM waves which are going to be having natural frequency of oscillations as that of the water molecules. Okay, so what you people should know is that, yes, selected to match the resonant frequency of water molecule, so that the energy from the waves is transferred efficiently to the water molecules inside the food. As a result, water gets heated, food gets heated up. Next, infrared rays are produced by what? Hot bodies, I said to you, right? Man, infrared vision, they'll put some glasses. Have you seen some YouTube videos? They are going to be hunting, right? They'll put on those night vision glasses. So it detects the thermal radiation. So basically they are called as infrared vision glasses. So those hot bodies are going to be producing those infrared waves or hot molecules, because they are going to be, when they are hot, they are going to be oscillating bigger. Amplitude of oscillations will increase. Okay, this band lies adjacent to the low frequency or long wavelength end of the visible spectrum, very close to the visible spectrum. Infrared waves are sometimes referred to as heat waves. This is because the water molecules present, okay, not needed. Yes, look, they are going to give you a question where which molecules are going to be absorbing the infrared rays. CO2, ammonia absorb infrared, and as well as water molecules also are going to be absorbing. So H2O, CO2, NH3 are going to be absorbing. After absorption, their thermal motion increases, that is, they heat up and heat their surroundings. Infrared lamps are used in physical therapy. Infrared radiation also plays an important role in maintaining the Earth's warmth. Okay, one more. Yes, this radiation is trapped by the greenhouse gases, such that the carbon dioxide and the water vapor. Infrared detectors are used in Earth satellites, both for military purposes and to observe growth of the crops. The electronic devices, for example, semiconductor light emitting diodes, also emit infrared and are widely used in remote switches of the household. Yes, man, this one. We use remotes to turn on the TV, right? Or if you have a fan which is going to be having a remote, when you press the remote, then the fan is going to rotate. So when you press, there will be a light which is going to be blinking. Sometimes you see it to be blinking, sometimes you can't see it to be blinking, right? Because if it is infrared, you won't see them. So what will be happening inside the remotes? Yes, you have infrared rays which are very close to the visible band. So that remotes are going to be producing those infrared waves. Okay, now visible, I don't need to explain this much, right? This is the most familiar thingy, right? Now, different animals are sensitive to different range of wavelengths. Our, like humans, are sensible to this particular these particular frequencies, which are going to be called as visible thingy. But for snakes, can detect infrared waves, and the visible range of many insects extends well into the ultraviolet also. For humans, we detect these frequencies. Snakes detect infrared. Wherever you see thermal, if you have seen any documentaries or something like that, what does snakes do? They'll show snakes and there will be a human, but the human is going to be in the form of thermal form. Like some portions are going to be red hot, some are going to be light hot. So thermal visions is what they say. So snakes have those thermal visions which are going to be infrared, but some of them have ultraviolet. We as humans will be able to see this range, and that is what is our visible thingy. Now UV, it covers wavelengths ranging from, okay, let us not talk about that. See, UV radiation is produced by special lamps and very hot bodies. Why did they say very hot bodies? If you talk about normal hot bodies, they produce IR. I am also producing infrared waves now. If you see through the eyes of a snake, you will see me as a body which is emitting heat. Okay. The sun is important source of UV light, but fortunately most of it is absorbed in the ozone layer. Okay, fine. Yes, UV radiation is absorbed by ordinary glass. So our glass, like glass doors or glass windows, are going to be absorbing majority of the UV. So if you want vitamin D, keep one thing in mind: you should not stand in front of a glass window and think that, okay, some sunlight is hitting me, so I'll get vitamin D. Most of the vitamin D is going to be due to what? UV rays. So if you are in front of the like if you are behind a glass window, light passes through the glass window, then reaches you. When it is passing through, glass window is going to be absorbing majority of the UV. So you get very less amount of UV. So keep that in mind, right? Welders wear special glasses, goggles, or face mask with glass. Okay. One more important. Yes, UV radiations can be focused into very narrow beams for high precision applications such as laser assisted in situ something keratomolysis, which is eye surgery. For eye surgeries, they say right, laser surgeries are being conducted, and what they are using over there? UV. And we know almost everyone these days have RO water in your house. Almost everyone is using RO. They are going to write RO plus UV. What is that? The UV light is going to be sent onto the water to kill all those bacteria and bacteria, as well as some germs and all those things, right? Okay, done. So one important thing is, in the eye surgeries, whatever people are going to go through, what will be used? UV rays are going to be used. This is one important thing. Next, almost done, man. Almost done. We are almost at the end. Afifa Muhammad, we are almost there. X-rays beyond the UV, where they are going to be produced. As I said, you already have the X-rays taught to you, right? So X-rays are going to be produced by, you can say, tungsten, molybdenum, these materials. For those materials, if you are going to send fast moving electrons, those fast moving electrons strikes these molybdenum or tungsten and X-rays are going to get produced. Right? These fast moving electrons, they strike and they knock out the electrons in the inner orbits, that is K shell, and then transition takes place which will emit some energy. So fast moving electrons colliding with tungsten, molybdenum, those kind of materials will produce X-rays. Yes. One common way to generate X-rays is to bombard a metal target by high energy electrons. Where they are going to be used? In diagnostic purposes and as a treatment for certain forms of cancer. And X-rays are going to be destroying the living tissue, so you don't need to worry about that. They can't ask any question on that. Okay, now last thing is gamma. Gamma is the most dangerous one, man. That's it. They lie in the upper frequency range of the electromagnetic spectrum and have wavelengths. Leave that. This high frequency radiation is produced in the nuclear reactions and also emitted by radioactive nuclei. That's it. Let us see what I have done. I have taken this from some book, right, where everything has been put together, but some of the points of NCERT have been missed, but some additional things have been given, like who discovered what and what are the applications and all those things have been properly bit segregated. So I will not be going through this one. I will give this PDF to you. It will be a good way to revise. These things are a good way to revise. Now let us look at the type of questions they have asked on this. Let us look at the type of questions they have asked. If microwaves, X-rays, infrared, gamma, UV, radio waves and visible parts of the electromagnetic spectrum represented by M, X, I, G, U, R, V, the following is the arrangement in the ascending order of wavelength. Following is the arrangement in the ascending order of wavelength. Ascending order. Smallest to the biggest. Smallest wavelength will be for whom? Gamma. So G. Which option is starting with G? Only one option. So what's the answer? C. So that's why I said you don't need to mug up. You don't need to mug up the whole thingy. Have a rough idea. Which one is going to have lowest wavelength? Gamma. Which one is going to have highest wavelength? Radio waves. So yes, radio waves. Highest. Ascending order. Done. Smallest to the biggest. Very good, Jayashree. Now look. Infrared, ultraviolet, X-rays, gamma rays. Man, basically I don't know. I don't know the exact values. So I'll choose. Smallest I'll give to gamma. 10 to the power minus 3 nanometer. This is 10 to the power minus 3 nanometer. This one is what? 400 to 1 nanometer. This one 1 millimeter to 700 nanometer. And then this one 1 nanometer to 10 to the power minus 3 nanometer. Now you use your common sense. Gamma is the most dangerous. So smallest wavelength. So pakka D should be equal to 1. Pakka D should be equal to 1. And then the next dangerous are X-rays, which is having lowest nanometer to 10 to the power minus 3. X-rays. So D should have 1. How many? See, D should have 1. So two options we have D as 1. Now X-rays should have 4. This. Done. This is the answer. Still, if you want to verify, infrared will have the highest wavelength out of all these 4. So which one is having highest wavelength? 1 millimeter to 700 millimeters. So infrared should be marked as 3. So A should be 3. Yes. So option B. This is how you need to do. You don't need to mug up. You don't need to mug up. Okay. Next. Last question of the day. Last question of the day. Almost done, man. Next 2-3 minutes it will be done. Next 2-3 minutes it will be done. Match list 1 with list 2. Right? Microwaves, gamma rays, Radio waves, X-rays. Gamma, I know. Gamma is going to be radioactive decay of the nucleus. Gamma is going to be radioactive decay of the nucleus. So B is going to be 1. How many options have B as 1? Only option C. For safety, I will verify one more. X-rays, right? I know one thing. Radio waves are going to be produced by rapid acceleration and deceleration of electrons in aerials. So C should be 2. Yes, B is 1, C is 2. Now A, microwaves. I already gave it. In NCERT also they have given klystron valve or magnetron valve or gun diode, right? So A is going to be 4. Then we are left with what? Obviously inner shells of this. So the answer for this is going to be what? C. Okay. Yes, we are done. We have completely covered everything in electromagnetic waves, man. You don't even need to refer to the NCERT. I personally have taken up the theory part of NCERT also. Numerical part has been given in detail. So this 2 hours or 2 hours 10 minutes, whatever the class you have gone through, you will get 4 marks. You'll get 4 marks. So go through the theory, go listen to this. You'll have 4 marks in your pocket. Solve as many questions as possible. Solve as many questions as possible. Bye. Good night. Good night. Okay, Arjun is asking a question. Arihant understanding physics or rank up physics MTG? Which one is better for JEE? Man, if you are thinking about having a lot of explanation given in a bit easier way, then Arihant understanding physics will suit you.